Hey guys, welcome back to the channel. Today we're doing a common emitter with emitter resistance. Now, just important things to note, we're going to be doing the small signal analysis, finding the voltage gain, input resistance, overall voltage gain, and the output resistance. Now, how do we know it's a common emitter? Well, we can see that the output's connected to the collector. Let's call this the collector, the emitter, and the base. And that the input is connected to the base. That leaves the emitter, which remember is always going to be the one with the arrow. That leaves the emitter with no input or output. That's how we name these. So, for example, a common collector, the input and output would be shared between the base and the emitter. The collector would have no input or output. That's why it would be called a common collector. So, in this case, also important to note, the arrow is pointing outwards of the transistor. That means we have an NPN junction, so all the currents will be flowing down. So first off, when we start off with the small signal analysis, we have to draw it in the small signal domain. That means we deactivate all DC sources and short circuit all the capacitors. So let's first start off by drawing the model. Remember, we're using the hybrid pi model for this. So in the base, we see that we have a base resistance. Then we have our voltage in terminal. And then, since we short circuit the capacitor, we have our sig and our voltage source. Now for the emitter, we simply have just an emitter resistance and we can ground that. Why do we only have emitter resistance? Well, we see that in the diagram, once we short circuit the capacitor, we find that this second RE becomes in parallel with the short circuit, which means we can simply just remove it. Now for the collector side, we see we have collector current or collector resistance in parallel with RL, where the output voltage is terminated. So another way to draw this is we notice RC is in parallel with RL, so we can simply draw this as one resistance RC in parallel with RL plus minus V out. So now that we have our circuit drawn, we can start performing computations. The first one we're going to do is the voltage gain. So for the voltage gain, simply, it's always going to be your output voltage over your input. Now for the output voltage, we see it's clearly connected to the RL in parallel with RC resistance. Now we know the resistance and we know what the current is. But it's also important to note that the current is not following the passive convention. It's leaving from the positive terminal. So we have to write this as negative beta IB RC in parallel with RL. So that's going to be our output voltage function. Now for our Vn, we don't really have an easy function like that we can just find. We'll have to perform a KVL around this closed loop. And that KVL will give us R pi IB plus RE IE minus Vn equals 0. So we can write that as equals Vn. Now also important to note, for our output, we have it as a function of the current IB. And for the input, we have it as IB and IE. So clearly what we can do here, since we know that IE is equal to beta plus 1 IB, we can simply just replace this IE with the function here to make everything in terms of IB so that the currents will cancel out. So we can write this new function for Vn as Vn equals IB R pi plus beta plus 1 RE. So this will be our new function for Vn. And now we can see, once we divide both of these, the IBs will just cancel out and we'll be left with given numbers so that we can easily solve this. So our V out over Vn is going to be equal to, now remember, we can cancel out these currents. So it'll be negative beta RC in parallel with RL divided by R pi plus beta plus 1 RE. Now this is going to be our final voltage gain. We see that it's negative, so we know that the common emitter with the emitter resistance is not going to be a voltage amplifier. Now for our input resistance. What we're doing for the input resistance is we're finding a Thevenin equivalent circuit from the eyes of the voltage input terminal. So basically we're finding a Thevenin equivalent circuit of this entire circuit right here. Now how do we do that? Well, the easiest way is to find we can simply just find the voltage function and an input current function, where the input current will be this, I in. So let's start with that. So let's find I in first. We know I in, we can simply just do a KCL across here. We'll call that node A. I in equals KCL A. So we can simply say I in equals, we know V in is going to be the node voltage across this node A right here. So we can say V in over RB, which represents this current going down, and then this current will simply just be plus IB. So this is going to be our function of I in. Now remember, we have to replace IB with something familiar, something that can make this a lot easier to solve. Now we found a function for IB right up here. Start this, we can bring this down, make it equal to IB equals V in over R pi plus beta plus 1 RE. Now simply we can plug this in and we'll find that I in. Once we plug this formula into our I in equation, we get I in equals V in multiplied by 1 over RB plus 1 over R pi plus beta plus 1 RE. So we're left with this. We notice that this right here inside the bracket is simply just 1 over these two resistances in parallel. So we can actually rewrite this as, so remember, 1 over REQ equals 1 over R1 plus 1 over R2. So we can simply write V in over R pi plus in parallel, R pi plus beta plus 1 RE in parallel with RB. So this is going to be a function of I in. We see that it's V in divided by I in. So we can simply just leave that V in here and the V ins will cancel out. So at the end, this will be our final input voltage. We can write R in equals V in multiplied by R pi plus beta plus 1. Let's just write this as I in for now. So we see R in equals V in over V in times R pi plus beta plus 1 RE in parallel with RB. Now simply what we're left with is the voltage ins cancel out and your R in will simply be R pi plus beta plus 1 RE in parallel with RB. Now that's going to be our final input resistance. This is the Thevenin equivalent resistance here for this entire circuit outlined in the blue. Now for the overall voltage gain. This computation actually becomes really easy now that we know the input resistance. We can also write this as V naught over V in times V in over V sig. Now how can we do this? Because V in over V in is simply just 1. So we're technically just multiplying the function by 1. But this makes it a lot easier because we've already computed the voltage gain here, which was AV, and now we can simply find this by performing a voltage division, because now that we have the equivalent circuit, we can write the new circuit as just a simple voltage source in series with R sig and the input resistance. Now and we know this is voltage in. Now simply just a simple voltage divider, V in equals R in V sig divided by R sig plus R in. Now we can see if we just divide both sides by V sig, we'll end up with V in divided by V sig. So now that we have a function V in over V sig and we know our voltage gain, we can simply just write the overall voltage gain as AV multiplied by R in over R sig plus R in. Now this is going to be our final overall voltage gain right here. Now finally, for the output resistance, what we're going to be doing is we're finding the Thevenin equivalent resistance in the eyes of the output voltage terminal. Now remember, in our original circuit, RC was not actually connected to the output voltage terminal. It did share the same voltage, but it was not connected to the terminal. So we'll have to redraw this as RC by itself in parallel with RL, where the voltage out terminal is. So again, we're finding a Thevenin equivalent resistance in the eyes of the output voltage terminal. Now, what we're going to be doing here is we're going to be adding a 1 amp current source. This is the easiest way to always find the output resistance. While when we find the input, we're simply just finding a function of V in and a function of I in. Now for here, since it's a 1 amp current source, there's going to be a voltage VT across it. Remember, resistance equals voltage over current. So this is simply going to be equal to the voltage across here, because anything divided by 1 is just itself, right? So let's replace this terminal here with the 1 amp current source, which has a voltage VT. Now from here, we have to find that voltage VT. And how can we do that? Well, simply, also really important, since we're adding a DC source, I'm sorry, I completely forgot about this for a second, but we have to remove the AC component. So this is what we'll be left with, R sig and just a short circuit across here. And we can also see that the R sig and the RB now become in parallel, so we can simply just write this as RB parallel with R sig. Now we can start the computation finally. So from this node here, we'll call this KCL at A. We can see that 1 will be equal to the current going through RC, which we know the voltage across that is VT since they're in parallel. So it'll be VT over RC plus beta IB. Now, as always, we never want to function in terms of the current, so we need to find what IB is equivalent to in this circuit. Simply, we can do a simple KVL. So what we have here is R pi IB plus RE IE minus RB in parallel with R sig IB equals to 0. Now, we can replace the IE with IB, so we get R pi IB plus beta plus 1 IB RE minus RB R sig IB equals to 0. Now, once we factor out IB, we can simply just divide everything inside that and see that IB would be equivalent to 0. This is what our function would look like. We can divide everything in this bracket and find a function of IB, which IB is clearly equal to 0. And if IB is equal to 0, then IC and IE will also be equal to 0, because IC is equal to beta IB, and IE equals 0 because it's beta plus 1 IB. So simply we can write 1 equals VT over RC. Now to find VT, all we have to do is multiply both sides by RC, and we find VT equals RC. And remember, our R out is going to be equal to VT, which is going to be equal to RC in this case. So this is our final output voltage, output resistance, and I hope you guys learned something from this.